Hello, and welcome to the Cabin Pressurization System lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: overview of the atmosphere and its components. What is pressure? How is it measured? And how does it vary with altitude? Oxygen at different altitudes, the concept of hypoxia, 737 NG pressurization system overview, typical flight profile, cabin pressure control and pressure control modes, cabin pressurization panel and cabin altitude panel selectors, pressurization protection and relief, and a lesson summary. Before we dig into the 737 NG pressurization system, we need to become familiar with some pretty important concepts about air pressure and the atmosphere. The atmosphere is a layer of gases that surrounds the Earth. It's held in place by the Earth's gravitational force. There are several layers that make up the atmosphere, but for the purposes of this lesson, we'll focus on the two layers that are closest to the Earth, the troposphere and the stratosphere. The troposphere extends from the surface until about 30,000 feet and contains roughly 82% of all the atmospheric gases. This layer is where most life forms are located and all the weather changes occur. The stratosphere, which follows the troposphere after a short pause known as the tropopause, is where most airliners fly. It extends from about 33,000 feet onwards to 150,000 feet. In the lower stratosphere, there is much lesser air than in the lower troposphere, and the air is also colder and relatively calmer. These conditions make the region between 30,000 feet to 40,000 feet ideal for airliners to fly, as skin friction drag over aircraft is virtually reduced to nil. All this air that extends from the surface actually weighs a lot. The total weight of the atmosphere is in the order of 5.3 times 10 to the 19th kilograms, and all that weight is exerting a force on top of us humans. This force, when limited to a specific area, is known as pressure. Now, we don't actually feel the weight of the atmosphere over us because our body is also internally pressurized. So pressure is essentially an exerted force per unit area. Under International Standard Atmosphere, or ISA conditions, air pressure at sea level is measured with a barometer and is either 29.92 inches of mercury, 1,013.25 hectopascals, or 14.7 psi. As we depart sea level and start climbing, the amount of air per unit volume becomes thinner. Therefore, the air density becomes lesser. With this, the air pressure also becomes progressively lesser. For example, the amount of breathable oxygen at sea level is approximately 21% of the total air. If the air pressure at sea level is 1,013.25 hectopascals, the mean pressure exerted by oxygen is 212.8 hectopascals. As altitude increases, air pressure reduces. Therefore, the concentration and pressure of oxygen also reduces to about 30% of sea level value at flight level 300, which is only 63.8 hectopascals. Naturally, this amount of oxygen is not sufficient to sustain life and permit cellular respiration. In simple terms, people would suffer from oxygen starvation if exposed to these pressure conditions in a condition known as hypoxia. Let's perform a similar analysis with the total air pressure at sea level of 1,013.25 hectopascals, as opposed to 265 hectopascals at flight level 330. If we convert both values to psi, or pounds per square inch, at sea level, the pressure is 14.7 psi, as opposed to 3.84 psi at flight level 330. The 737 NG cabin pressurization system allows the airplane to operate at altitudes where oxygen density is not sufficient to sustain life. The pressurization control system is a sister of the air conditioning system, which is comprehensively discussed in the respective 737 NG lesson. The pressurization system uses bleed air that is cooled and filtered to provide the flight deck and passenger cabins with fresh air. For the most part, pressurization is achieved by sealing the cabin when the aircraft's altitude increases, thus avoiding contact with the external atmosphere. Air is, of course, modulated and disposed overboard the aircraft while fresh new air enters it, in order to maintain a constant cabin pressure. Because the air outside an aircraft flying at, for example, flight level 350 is so scarce, any form of leakage or hole in the cabin would cause a massive flow of air outward. Remember that air always flows from where there is high pressure to where there is low pressure. The more the pressure difference between the cabin and the external air, the worse the disaster would be in case a hole or crack in the cabin were to develop. An example of this was United Airlines Flight 811 in 1989, where a failure due to cargo door design flaws caused an opening that led all the pressurized air to rush out of the aircraft, carrying with it several rows of seats and the lives of 9 souls. This event is known as a rapid or explosive decompression. It's important to understand the pressurization mechanism on board the 737NG to minimize the risk of this occurring to you during your flights. An easy experiment to picture how bad an explosive decompression can become is this. Insert a spoon of cooking flour, which is the passengers, into a balloon, the aircraft. Blowing up the balloon and tying a knot to it is somewhat equivalent to pressurizing an aircraft. Whenever you're ready, find a needle, poke the balloon, and observe what happens. We take no responsibility if your face is now covered in cooking flour. Moving on. In order to maintain a comfortable amount of air and oxygen for the passengers and crew, the pressurization system pressurizes the cabin to a safe altitude. The bleed air system and air conditioning packs introduce air into the cabin. But a cabin pressure control system is in charge of controlling the rate at which air flows out of the cabin by closing and opening a valve in the aft fuselage, known as the outflow valve. Cabin pressurization also has a relief system that is provided as a protection mechanism if the pressurization control system were to fail. The cabin may be saved from cabin overpressure and cabin negative pressures. Aircraft pressurization may be controlled either automatically or manually. The automatic mode control has 2 submodes, automatic and alternate, for built-in redundancy in case one automatic mode fails. A pressurization mode selector located within the cabin pressurization panel in the forward overhead allows the pilots to choose between automatic, alternate, or manual pressurization control. When the pressurization mode selector is placed in the automatic position, the airplane is automatically pressurized for all the flight phases. This is achieved with a cabin pressure controller, or CPC. To provide system redundancy, the automatic control system has 2 CPCs, but only one of them works to pressurize while the other is on standby. With each new flight, the pressurization system switches the active CPC in order to maintain an equal amount of wear and tear between both. Essentially, during automatic control, the CPCs compare the target cabin pressure with the actual pressure at the CPC sensing ports. If there's a difference, the CPC commands the opening or closure of an outflow valve in the lower right aft fuselage, as we mentioned earlier, in order to control both the cabin pressure and the rate of change of pressure. In either the automatic or alternate mode, 2 valves must be preset before takeoff into the pressurization control panel: flight altitude, which is the cruising altitude, and landing field altitude, which is the destination altitude. The outflow valve is a form of exhaust for the majority of the air that is circulated through the passenger cabin in order to maintain a desired cabin pressure. Air is extracted from the cabin through grills at foot level, ducted around the aft cargo compartment, and then discharged overboard the aircraft. As the warm passenger exhaust air flows from the cabin to the outflow valve, It serves as a heater for the elements in the aft cargo compartment. Moving on, the automatic pressurization control mode is designed to pressurize the cabin to 8,000 feet when the 737NG is flying at its maximum certified ceiling of 41,000 feet. This level of pressurization produces a differential pressure between outside air and cabin air, which must match the schedule outlined in the following table. The current cabin pressure differential and cabin altitude can be read off an instrument in the cabin altitude panel in the forward overhead. The inner scale indicates the current cabin altitude in feet, and the outer scale indicates the differential pressure between cabin pressure and external pressure. These instruments must be used to check that the flight pressure differential is effectively within the limitations stated in the table. Cabin rate of climb may also be read immediately below the cabin differential pressure indicator with the cabin climb instrument. Many unwanted conditions may cause one or both CPCs to become inoperative, thus triggering an amber auto-fail light in the cabin pressurization panel. These conditions are power loss, cabin altitude rate of change that is too high, greater than 2,000 feet per minute, cabin altitude is too high, greater than 15,800 feet, cabin differential pressure is too high, greater than 8.75 psi, wiring and electrical failures, outflow valve actuator failures, either CPC having a failure. When any condition triggers the auto-fail function, a master caution and air conditioning annunciator is presented. Along with this, a green color alternate light illuminates to show that the backup pressurization system is active. If any active CPC fails, the system automatically switches to the backup CPC. If both CPCs were to fail, the alternate light doesn't come up because the system can no longer transfer pressure control to an operative automatic controller. It's clear that the level of system redundancy is high because if any form of depressurization were to develop, the flight crew would be forced to rapidly descend the airplane down to an altitude. Furthermore, the pressurization system may even be controlled manually, as we mentioned before. To do this, the pressurization mode selector must be changed to the manual mode. When this happens, the manual green light illuminates in the cabin pressurization panel. The outflow valve opening and closure is now controlled manually, and both automatic CPCs are bypassed. To control the outflow valve manually, the pilots use the outflow valve switch in the cabin pressurization panel. This switch is spring-loaded to center, but has the following positions. Close. When the pressurization mode selector is in manual, it progressively closes the outflow valve. Open. When the pressurization mode selector is in manual, it progressively opens the outflow valve. A good way of remembering how to operate the outflow valve switch when pressure is manually controlled is moving the switch towards the center of the aircraft keeps the air inside. The full range of motion of the outflow valve takes around 20 seconds. To make things slightly easier when manual operation is in place, there's a placard in the cabin pressurization panel that shows the standard settings for cabin altitude versus cruising level. Moving on, we've discussed a couple of pressurization modes and how their operation works. It might be difficult in the beginning to grasp the operation of the CPCs, pressurization modes, and all the components. So let's now move on to something a bit simpler. We mentioned earlier that the automatic pressurization control modes maintain the cabin pressure during all phases of flight. The cabin pressurization system is concerned about the following flight phases: ground, takeoff, climb, cruise, descent, and landing. Each flight phase is defined by a specific series of actions, and each has a determined set of cabin pressure limits, either in terms of pressure rate of change, pressure differential, or cabin altitude. Let's talk about each one in particular. On ground, the airplane is unpressurized and the outflow valve is fully open. The system senses the ground condition when the air-ground system senses compression in both main landing gears. Engine N1 is lesser than 50% for 1.5 seconds or more. Engine N2 is lesser than 84% for 1.5 seconds or more, or when both engines have been shut down. Engine parameters are extensively discussed in the 737 NG engines lesson. To start the takeoff phase, the pressurization system must recognize the following conditions. N1 on both engines must increase past 60% for 1.5 seconds or more. N2 on both engines must increase past 89% for 1.5 seconds or more. During the takeoff phase, the cabin is pressurized to 0.1 psi below field elevation by slowly closing the outflow valve. The reason for this is to prevent an uncomfortable pressure bump for passengers when the airplane rotates. Also during the takeoff phase, the cabin altitude rate of change is in the order of 350 feet per minute. Once the air-ground system senses that the left and right main landing gears have left the ground, the climb phase starts. The pressure differential between the cabin and airplane altitudes is proportionally controlled. By increasing the airplane altitude at a rate that is in proportion to the airplane climb rate, the total cabin altitude change is kept to a minimum, thus giving the system and passengers a better response to pressure changes after takeoff. If there were any form of depressurization during climb, the maximum rate of cabin altitude change would vary between 600 and 750 feet per minute, depending on specific aircraft. As and when the airplane altitude increases, the cabin altitude also increases, and so does the pressure differential. To understand the cruise logic, let's go back to the flight altitude selector in the cabin pressurization panel. The pilots must enter the expected cruise level in the flight altitude selector, which allows input between 1,000 feet and 42,000 feet. While the aircraft is climbing and the external air pressure decreases within 0.25 psi of the flight altitude selection, the pressurization system switches to the cruise mode. In this mode, the cabin altitude is maintained according to the pressure schedule we talked about previously. If the aircraft were to ever descend below the flight altitude selection, an off-schedule descent light will illuminate in the cabin pressurization panel, indicating that the aircraft descended before the planned cruise altitude. This may occur, for example, if a flight is aborted after takeoff or during the climb phase. If the flight occurs between 18,500 feet and 28,000 feet, the target pressure differential is 7.45 psi. If the flight occurs between 28,000 feet and 37,000 feet, the target pressure differential rises to 7.8 psi. Finally, if the flight takes place at or above 37,000 feet, the target cabin pressure differential becomes 8.35 psi. If at any point the cabin altitude increases past 10,000 feet, a cabin altitude warning horn will sound. To extinguish this horn, the Alt Horn Cutout button in the cabin altitude panel must be pressed. If the flight takes place at any altitude below 18,500 feet, the pressurization system will directly pressurize the cabin to the landing field elevation. During cruise, any deviation from the selected flight altitude may cause the pressure differential to rise as high as 8.45 psi to maintain a constant cabin altitude. However, when the intended landing field elevation is higher than 8,000 feet, there are different sets of rules for pressurization. If the landing field elevation is greater than 8,000 feet and the flight is lesser than 60 minutes, the cabin altitude during cruise will be equal to the landing field elevation. If the landing field elevation is greater than 8,000 feet and the flight is longer than 60 minutes, the cabin altitude during cruise is maintained according to the cruise pressurization schedule. 20 minutes before landing, the pilots must enter the actual landing field elevation so that the cabin altitude climbs to that same value. Once the aircraft has commenced its descent and the external pressure increases to 0.25 psi or more than the flight altitude or cruise selection, the pressurization system senses the start of the descent phase. This is when the landing field altitude selector comes into the equation. Before takeoff, the pilots must also enter the landing field altitude in the landing field altitude selector, located below the flight altitude selector in the overhead panel. This is done so that during descent, the pressurization system pressurizes the cabin to 0.15 psi below the landing field altitude selection in order to avoid a pressure bump from discomforting passengers during landing, similar to how it's done during the takeoff phase. In this phase, the cabin altitude rate of change is in the order of 500 to 750 feet per minute, depending on the aircraft model. Once the aircraft is landed and the air-ground system senses that the airplane is in the ground mode, the pressurization system depressurizes the cabin at the rate of 500 feet per minute. When the cabin pressure is the same as the local ambient pressure at destination, the outflow valve opens fully. We're almost there with the pressurization lesson. There are only one or two more things that are important to keep in mind. Early on in the lesson, we mentioned that the cabin pressurization system has a relief mechanism that is provided as a protection mechanism in case the pressurization system were to fail. Two relief valves protect the cabin from overpressurization and negative pressures. Two positive pressure relief valves, located aft on each side of the outflow valve, protect the cabin from overpressure. If the outflow valve were to fail, air would start collecting within the cabin and differential pressure would increase. When this occurs, the positive pressure relief valve bleeds cabin air overboard so that a maximum pressure differential of 9.1 psi is restored. Once the conditions are normal, the positive relief valve closes. On the other hand, a single negative pressure relief valve located aft on the lower left fuselage protects the airplane's structure from being damaged by negative pressure differentials. This is especially important during a rapid descent, such as after a rapid decompression. When pressure outside the aircraft is 1 psi more than the cabin pressure, the negative relief valve opens. Notice that this valve is independent from the 737 NG pressurization system, and it requires no crew action. We've talked extensively about cabin air pressurization during this lesson. We started by talking about the concepts of atmosphere and pressure. Then, we dug into the 737 NG cabin pressurization system. And finally, we spoke about a few protection mechanisms that are available. The overall built-in redundancy in the system is fairly good. Under most scenarios, there's always a backup form of maintaining pressurization in the cabin. And even when all the automatic mechanisms fail, cabin pressure may be controlled manually. For this reason, it's important that you fully understand how and when to operate the outflow valve, so that your sim passengers don't feel the lack of oxygen in their bodies. Hypoxia is a very dangerous condition. In numerous cases, there have been pilots incapacitated because of not being able to deal with it, and no emergency is worse than a pilot incapacitation. This lesson covered the following topics: overview of the atmosphere and its components, pressure definition and measurement, with the United Airlines example, oxygen at different altitudes, the concept of hypoxia, 737 NG pressurization system overview, typical flight profile and flight phases, cabin pressure controllers, CPCs, and pressure control modes, cabin pressurization panel and cabin altitude panel indicators and selectors, pressurization protection and relief, plus a lesson summary. This was the last lesson in the groundwork air system section. As you can see, bleed air, air conditioning, and the pressurization systems are significantly different. But the three of them must work in harmony to keep passengers and crew comfortable during flights. Stay tuned for the following lesson, where we'll talk about the 737NG fuel system. Until then, throttle on.